Thank you. Can you guys hear me okay? The microphone's en route, I think, so I'll talk loudly until then. Thanks, Berga. That was embarrassing. And I just, yeah, it's like 15 years collapsed into a few seconds. Sounds impressive when it's not. So this is my first time at UCR, and I have to say I'm a little embarrassed that I didn't know about all the wonderful stuff going on here. I actually think that this is, I mean this in a nice way, it's sort of a problem. Like, we don't really talk. Like, I'm like an hour from you guys, and there's a lot of collaboration we could and should be doing. The same is true with Santa Barbara. I mean, my parking pass works here. Like, I could just park. Like, we got to figure this out somehow. I don't know how, but we need to be better friends. So thank you for a wonderful day. What I want to talk about is, in fact, this quantum apocalypse. I'm a bit of a worrier. And I first want to sort of, I guess, tell you what I mean by this. Like, basically, I'm sure you guys have heard about all the hubbub about quantum right now. Everybody and their brothers jumping into it. And if we don't manage this right, it's going to be really bad for the field, I think. And I want to talk about that. I want to talk about sort of, why is everybody sort of jumping into it? I'll just sort of very gently introduce you to the ideas of quantum advantage, mostly in light of quantum computing. And then I want to talk about how I see this all going wrong. And to keep it from going wrong, we as physicists and chemists especially need to be working on next generation devices. So not just trying to jump on the bandwagon and do what people are doing now, make it better, because the stuff we're already doing will never work. Like, that's a fact. The stuff Google's doing, it just won't work at the scale we really want it to work. Right? So we need new qubits. We need the transistor, if you will, of quantum computing. I'll tell you about our work there. We sort of have 3 projects trying to develop new qubits, but I'm not even sure these are going to be good enough. And so I'm going to leave you with sort of my dream and sort of a challenge to all of you of what we actually need in this field. So I'm going to talk about a lot of different projects today, and they're funded by different sources, and we're really thankful for that funding. Okay, so, this doesn't work. So this quantum industrial revolution, you guys have heard this buzzword. You heard quantum 2.0, they're calling it. I heard someone say quantum 3.0 the other day. Didn't know there was a 2 yet. But so why is everybody talking about this? Well, just to sort of take a step back and frame the problem, I think, in a very general way, you can ask, what was it that took us from this life to the life we have today, right? Now, you can make an economists and historians really mad, but I think the answer is simple. I think it was basically F equals ma, right? Newton and his cohort, like the foundation they laid for science, I mean, maybe, sure, there were other factors at play, but it was certainly the blueprint that allowed us to do that, because science told us what was possible and how to do it, right? Now, what's interesting about that, and the reason we're here today, is that it's science that also tells us what's impossible, right? We're not out trying to build perpetual motion machines, because we all know that would be a waste of time, right? Similarly, though, we know that quantum mechanics allows certain things to be possible that we thought were impossible, right? To put it another way, the universe is totally fine with me doing some things that Newton said I couldn't do, right? Or classical thinking said I couldn't do. And so we ought to reinvent all of our technology in light of that to take advantage of these extra features, right? And so that's the dream that's going to take us to sort of our utopian future, right? This is the pitch of the quantum industrial revolution, where we have flying cars and robotic dogs that you still have to walk for some reason. Right? So I sort of believe this, but it also makes me really, really mad, because the truth is, we've been in the age of quantum-assisted technology for a long time, right? And as someone working in that field, I don't know, it feels a little maybe short-sighted, right? You guys have probably heard about atomic clocks, magnetometers, gravity gradiometers. These are things that take an atom, split its wave function, recombine it to measure gravity, right? You can buy this thing from a company for like 10 years. Right? There's random number generation, quantum cryptography, quantum communication. I mean, this is a rack-mountable device you can use to generate or to distribute keys for encrypting things using quantum mechanics that makes it secure, right? So given all this, why is it suddenly now quantum 2.0 or quantum 3.0? And the answer, I think, is because this field that's been pushing towards quantum computing is starting to get interesting. Now, I would caution that starting to get interesting is very different than starting to get useful, and that's the thing we have to be careful with, right? But let me tell you about sort of why quantum computing is sort of powerful in one example, and sort of why we're starting to get to the point where it's useful. And I want to do that with our favorite system as physicists, right? If we're talking about quantum, let's talk about a spin 1/2 particle. It can be 0, we'll call it 0 and 1, so it sounds more computery instead of spin up and spin down, right? We know that this thing can be in a superposition, right? We also know that, say, if I have two of them, they can be entangled, right? And so the total wave function that I have to keep track of for a system like this has 4 numbers in it, right? It can be in 0, 0, 0, 1, 1, 0, 1, 1, right? 2 to the n states because they could be entangled. Now, suppose I'm able to implement some sort of Hamiltonian on this spin system. And let me just pick a spin Hamiltonian because that's convenient, and you probably have looked at this before. We have a term that's like a spin-spin interaction, maybe some sort of global interaction. As you'll see, the things we're building in the lab allow us to control these couplings so that we can make it whatever we want. We can make it time dependent. Same thing here. Yeah, sure. Okay.
Thank you.
Got it. And so what we can do is if we have some device like this, we can take a Hamiltonian and just run it like that. And we start in some wave function and see how that evolves, right? And you can learn something about that Hamiltonian. Maybe, as I'll talk about in a second, maybe you can make that Hamiltonian useful for something, right? Right, you look at this and say, what's it going to do? Right, there's 4 numbers. I can actually do this by hand, like as long as these things aren't changing too much in time, right? And if they are, I'll just do it on a computer. That's trivial. So what happens is something pretty spectacular. That's because quantum systems can be entangled. As I scale up, this is 30 of these spins, right? Still a very small number. Not a condensed matter physicist, considering some quantum many-body problem, 30 electrons ain't that many, right? So this would be a very toy model. But already at this point, we go to write down this wave function, and guess what? There are over 1 billion terms, right? There's 2 to the 30 terms because this register can be entangled. So now if I go to do this, you start to run into computational problems. You can do this on a laptop at this sort of level, sort of maybe kind of depending on what you're asking. If you go a factor of 10 more to 300 qubits, still a very small machine, there are more terms here than there are known atoms in the universe. Right? So that somehow seems like a practical problem in terms of memory consumption. Is this okay like this? Is it too loud? It's okay? Okay, perfect. Oh, that's what you do. And so what the advantage is, if you could build a quantum computer, you only need about 30 qubits. Maybe you need a little bit more for error correction, but it's something that scales hopefully linearly to this number. And so what I can do is take this Hamiltonian and run it on my quantum computer and see what happens. All right, as physicists, we're all like, that's great. There's a lot of quantum many-body problems I'd like to know about. I'd like to learn about this Hamiltonian and others, and I can quench these things, take it through a phase transition. I'm going to learn all kinds of stuff, right? But why are the governments super interested in this? Well, part of the reason is I'm only telling you about one version of quantum computing, not sort of the gate-based version, which is a little, it's a little more obscure to see this speed up. But the other is that you can write a lot of Hamiltonians in a form like this, if you try hard enough, right? You could do some Jordan-Wigner transformation to take it from sort of particle hole excitations to this. And then, for example, that Hamiltonian is very useful for calculating molecular structure. So it turns out these devices are probably really good at calculating molecular structure, right? They can be used maybe for optimization, and all you have to do is sort of write your problem in terms of this Hamiltonian and let it go. All right, so that's one version, and hopefully you can see a little bit of what's out there. And so I want to be careful in what I say, but I also don't want to sound too negative. I think we as physicists should be very excited about what's happening in the field, because I think we're already seeing this. Quantum many-body systems are pushing the limit, or we're able to build controllable quantum many-body systems beyond what can be calculated easily, and maybe very soon, if at all, right? Because every time you add one more qubit, the calculation would double for a classical computer, right? So very quickly, you run past these things. And so I actually think that we're going to see major developments in quantum many-body physics. Right? This is total speculation, but I'm hoping that there's going to be like a hydrodynamics of entanglement, if you will, sort of theory that comes out of this, because we're going to have these quantum systems and we can take them through phase transitions and look at correlations and just measure that in real time. So I think all of us should be really psyched about this. You know, the question of is it going to be useful is a different question outside of physics. Right? There is some hope for chemistry, as I mentioned, for these for calculating molecular structure. Things like, you know, this is like, I think, penicillin. If you try to do this in some sort of full CI calculation, it's basically impossible. But on a quantum computer, it scales quite nicely. Oh, I did want to mention this briefly. I added this at the last minute. I don't know if you saw this, but this appeared on NASA's website for a couple hours earlier this week, and then it disappeared. I don't know if it's back up or not. But so the Google team, which is based in Venice, just towards me a little bit in LA, and in Santa Barbara, posted this paper for a few hours where they claim to have demonstrated quantum supremacy. What is quantum supremacy? It's a word Google made up about 2 years ago to sound really cool. And it's supposed to, like in a nutshell, it's basically they're going to do something that a classical computer could never do. And so they ran a basically random algorithm that was made to be really easy for a quantum computer but hard for a classical computer. And they claim that it took about 300 seconds on their quantum computer, and it would take 10,000 years to simulate this on the state-of-the-art supercomputer. Now, probably this algorithm is completely useless. And this has not really been peer-reviewed yet. I've only had time to sort of skim it, but you can see that like these things are actually starting to pop up. So I'm not endorsing this, but just telling you. Okay, so given that and given all my excitement, like why am I worried? And the answer is the politics of this. So, we've been doing this for a while, but suddenly now everybody is doing quantum. And why is that? Like the answer is probably China, to be completely honest with you. 2 years ago, they did this experiment where they used a satellite to distribute a key using entangled photons. And it sort of got people nervous. From a science point of view, this wasn't that interesting. The technology to do this has been known for a very long time, and people have done it over shorter distances. Nobody bothered to do it on a satellite because it probably took them like 2 days to distribute the key. It was so slow. I actually don't know how long it took, but I'm sure it took a long time. But it got people thinking. And then China doubled down and said, we're going to invest 10 to, some estimates say $50 billion to build a quantum computer. Right? You have the New York Times worried about, oops, I messed my best joke up. You didn't see that. You have the New York Times worried about there are not enough quantum computing researchers. What are we going to do? China's going to take over. And so last year, everybody's favorite guy, who clearly understands what he signed, like what the hell is this thing? Signed the National Quantum Initiative Act, which will invest, depending on how you count, like a couple $billion into quantum mechanics. And so now everybody and their brother is rushing to the gold mine. At the same time, you have IBM, Google, Microsoft, all publicly declaring that they think the future of computing is quantum computing. Each one of these invests, I believe, about 10 to the 8 dollars per year into this, which is a lot of money. From a research perspective, if we had that, who knows what we could do. You have a bunch of smaller companies like IonQ, which are at the 10 to the $7 per year level, building these things. And so, my worry is that given all this politics and all the spotlight that's now on this, that if we don't deliver something useful in 5 or 10 years, there's going to be a little bit of a backlash, right? That, if you are an investor, you're probably worried about this happening, which we're probably about to the red part, I guess. And so the question is, how do we prevent the bust from this boom right now? We need to spend wisely on what we're doing. And from what I've seen so far, we're not doing that. And there's sort of 2 ways I think this all goes bad. The first is actually pretty mundane problem, and it's one we should address. And that is, there are very few people that are actually able to do this stuff well. Talking with a company, I guess I can't say who it was, their research said that they believed there were 788 experts in quantum information in the world. And they needed to hire 500 of them. So we got to figure that out. And that's something we at the UC level, I think, especially because we are one of the powerhouses of education in the country, we have the capacity to educate a lot of people. We need to be talking about this. We're thinking about it at UCLA, and I'd be happy to talk to you guys about that. The other one, I call it the Boromir fence. And that is a lot of people think this is easy. And it's not. We have a lot of people rushing into it, doing things that, in a couple of years, I think they'll realize maybe we shouldn't do. And so one of the things I want to do is sort of tell you about the pitfalls of the technology we have right now and ask for help in ways that I think people can contribute. All right, so let me do that by just highlighting the 2 leading technologies, at least leading at the industrial level. So Google is based on superconducting qubits. Basically think of an inductor and a capacitor. You get like a harmonic oscillator. You make it a little nonlinear so that the level spacing isn't equal. And so then you can just address the first 2 levels and call that a qubit, right? Without coupling to the 3rd one. Trapped ion qubits are probably the most developed in terms of fidelities. There's a company called IonQ developing that. And there the qubits are internal states of the ions. All right? They each have their own advantages and disadvantages. For the Google thing, it looks like a computer. Right? It looks like something I can pattern and make. And so all of us, including those of us who do stuff like this, sort of thought, of course this is how you build it. Right? But as that's progressed, what we found is that because these things are man-made, they're not identical. And especially for this technology, that's a problem in scaling up because they need to be close enough to each other to sort of share photons. All right? And so that's one of the big problems. It's a control problem. And it makes it look like it may not actually be scalable after all. Trapped ion qubits, they're all identical. I mean, they're even indistinguishable. You can't tell a difference between any ytterbium atom in the universe and another one. But the scalability looks hard because this doesn't look like a computer. Like humans aren't good at building this sort of technology up yet. We haven't quite figured out how to do that. And so what I thought I would do was just focus on this one and sort of show you some of the problems you run into as you try to scale up to a larger and larger system. All right, to set the stage, we can do things like 50 qubits right now on sort of both of these technologies, roughly speaking. But to really run, and that's, by the time you're to 100, you're way past what you can do classically. But to really be useful for like gate-based quantum computing, you probably want thousands of qubits. And if you want error correction, you probably need even more, right? So how do we go from where we're at now to there? And you can see the problem by sort of focusing on trapped ion qubits. So this is a string of, I think these are ytterbium ions. At UCLA, I didn't really go into details of how we trap these. These are ions. We use some voltages and can trap them. You can probably take my word that that might work. Some electric fields. And we use lasers to cool them down. I can tell you more about laser cooling. If you don't know about it, just assume it's kind of magic. I can shine a laser at them and make it really cold. Right, basically at 0 Kelvin. I can cool this thing into the ground state of its motion, in fact. Right? So why do these things form a line? Well, my trap is sort of a cylinder with 2 harmonic oscillators that are very tight this way and weak this way. So they all want to go to the center, but because they repel each other, they're ions, the lowest energy configuration is to line up like this. And of course, well, these are about 10 microns. These are a few microns apart, so it's easy to see them. This is just an optical image. And you see them because they're scattering light from the lasers that are cooling them. All right, so this is a ytterbium-171 atom. This is the internal states. So it's very much like a hydrogen atom. There's an S ground state and a P excited state. Unlike hydrogen, there's some metastable states over here. And we can define a qubit in here by just picking two of these levels. And there are different ways of doing it. I want to pick these two. This is not really what people do in ytterbium, but it's the easiest to explain what I'm going to tell you. So we'll take these two states, this ground state and this metastable state, and we'll call that our qubit. Right? So we have a ground state and excited state. And now let's just go from a bunch of these and just look at two. Right? So these guys have I now have two of these. And if I think about their normal modes, there's like a center mass mode and a breathing mode, right, that they have here. And let's just focus on the breathing mode here. So I can cool this thing so low that it's in the ground state of motion, and I'll denote that by N. I'll sometimes call that the phonon number, right? And so because I have this ladder of states here, over here I actually have a ladder of states here. So this would be G0, G1, G2, and so on. Right? So how do I use this to entangle them, right? You can see already that they're sharing this phonon, so that's going to be my resource for making them work together. So I could take a laser, and this may, for Berger, this may not be this is not how you really do it, but it's, I think, the easiest way to show it. Suppose I was in this n equals 1 state, so I had one motional quanta here, and I'm in the ground state. And I apply a laser here, and I do what we call a pi pulse, which just transfers that population to the excited state. Right? So what I've done is I've taken what I would call GG1 to EE0. So I'm in the ground state with 1. I've taken it to EE0, right? Now I could do, suppose my population had instead been in the ground state. That laser does not have the right frequency to make this transition, and so my pi pulse does nothing, right? And so you could imagine if before I applied the laser, I put it in an equal superposition of these two states. When I apply the laser, I then make a Bell state. I make GG plus EE, right? And if you can do this, you can basically build a quantum computer, right? If you can make a Bell state, I mean, it's more or less, that's the NAND gate of a quantum computer, if you will, all right? There's certainly a lot more details, and this is not how you would really want to do it, but I think it sort of gets the essence of what you're doing. All right, so where's the problem? Well, I want to grow this now, right? And this is like 8, I want to go to 100, but even at 8, I now have 8 normal modes. So I come here to this spectrum, and it's very congested, and it's a control problem. My gates take longer because I have to resolve these transitions, right? And there's just a lot more bad things that can happen. And so what people have proposed are sort of 2 paths forward. One I'm not going to talk about, which is putting this on a chip and shuttling the ions around. I'll mention it later. The other is to build what's called a quantum network. And the idea is let me take as many ions as I can shove into one of these modules, and then I'll hook them all up with fibers. All right? So maybe I could get 100 qubits in one of these or of order that. And I'm going to hook fiber optics between them. And what I can do is I can collect photons that these things emit and use that to entangle, say, these 2 ions right here. And then once I've done that, I can then entangle the rest of the register with it. So I can grow my quantum computer by this remote entanglement, bringing in new registers. Okay? So the problem with that is that right now on trapped ions, the 2-qubit gate speeds are of order 100 microseconds. You can do faster with some things, slower with some things, but to do it well, it's something like this. The remote entanglement rate is about 5 hertz, right? And the reason is you basically have to get lucky and a photon has to go into an optical fiber, which is really hard to do. And so this sort of scaling up, this is a roadblock to it. And so we started a project a few years ago aimed at improving this. And I'll tell you about that now. It's sort of the first step into sort of new qubits, if you will. So this is a project I've been doing with Wes Campbell, who's also a professor at UCLA. Some of you may know. Justin's a great grad student, and David was the first postdoc on this, who's now at the Air Force Research Lab in Rome. Barium-133 is the qubit we're using. You can see from the structure, it's very much like the ytterbium thing I used earlier. But for details I won't go into, people call it the Goldilocks qubit, or some people do. And that's because it's sort of just right properties for everything. It's got just enough hyperfine structure, just right wavelengths, so on and so forth. But no one had ever used it. So why would no one ever use this thing that is, maybe an ideal qubit? Dave Huckle summed it up best. He said, there's only one problem with it. There isn't any. And the reason is, it's radioactive. It has a 10-year half-life, and it's all gone. It turns out, though, that it's a common man-made isotope. It's really good for calibrating a gamma ray spectrometer. And so you can get it very cheaply. And so a couple years ago, we demonstrated that we're able to trap and laser cool it. And this is the first picture on Earth, I guess, ever, of 133 barium ion. Maybe some aliens have pictures before us, but this is the first one we got. It was fun from an atomic physics point of view because there's all this spectroscopy that was never measured, and that's like, we don't get to do that anymore. We don't get to measure transition, like atomic spectroscopy. And so since then, we've been working on demonstrating it as a qubit. Let me tell you sort of where we're at with that now. There's a couple qubits you can define in this. One that's really nice is in the ground state. We can take this F equals 0 level here. F is the total angular momentum. It's the coupling of the electron spin with the nuclear spin. Barium-133 has a 1/2 nuclear spin. That's part of the secret sauce. So you get this F equals 0 level, which is special. And then you get an F equals 1 level, right? You get, half and a half is 1 or 0. And so we can pick two levels here and make a qubit. They're separated by about 10 gigahertz in energy, which is super convenient for using microwave rotations. And to build a quantum computer, there's sort of 4 criteria. You should remember, people cite these all the time, these DiVincenzo criteria. This is sort of my version of them. The first one is it's got to be scalable. You got to be able to build a lot of them. The other is you need really good spam. Spam is jargon for state preparation and measurement. It means I got to be able to prepare the qubit in a state and measure it, knowing I have to be able to do that really well. You need to be able to do these gates I talked about, entangling gates, single qubit gates, and you need great decoherence times, right? Atoms sort of always sort of check this off. I mean, people have stored information in these states for 10 minutes, right? So that one's not so hard. The scalability, the whole point of this I'll come back to, is that maybe this is better for remote entanglement. And so let me tell you about what we've been doing recently of just trying to get these two things under control. So the way we do state preparation and measurement is we engineer it so that if the atom is in one of the states, when we apply a laser, it scatters photons over and over. That's why you can see it, right? We're just collecting fluorescence. If it's in the other state, it doesn't. And so what you can do is just by applying a laser, counting how many photons you see, you can make some determination of what state you're in, right? This is the projective measurement. And to give you an idea of what that looks like, if you do it about 300,000 times over and over and over again, you can make this histogram. Where if you're in the 0 state, which we sometimes call the bright state, on average you get about 30 photons. If you're in the 1 state, on average you get a few because there's scattered light, there's dark counts, there's experimental realities. So you could set a discriminator around 10. If it's above that, you say that I was in 0. If you're below that, you're in 1. Now, if I were to plot this on a log scale, you would see that there are errors here. There are places, you can't see them on this scale, where the blue show up here and the yellow show up here. So those are readout errors, or they could be state preparation errors. You can't really separate them, so we just call them spam errors because it could be a state preparation or a readout error. But when you do this, we're able to do this. So we quote fidelities, which 1 means we can do it perfectly, right? It's basically a percentage. And the average fidelity, if you will, is about 3 nines and a 6 or 7. That means that if we do this 10,000 times, on average, we expect to mess up about 3 times. Right? To put that in perspective, this is the best qubit in the world by at least a factor of 2 of any type. Right? And it's all because of this sort of Goldilocks nature of barium-133. And we believe we're going to be able to push this another factor of 10 or so, which makes it a lot easier to do error correction. Okay, so since then we've been, playing around with these single qubit gates. This is sort of the canonical ion trapper plot of showing Rabi flopping between the qubit states. So we measure, and if you're if the blue point is here, that means you're in the 0 state. Up here, you're in the 1. In between, you're in a superposition, and we're just affecting that with a microwave drive. What's fun about this and like super satisfying as an experimentalist is because the spam is so good, these actually go to 1, right? They go between 0 and 1, and I don't know, it just feels, it's just super satisfying. I can't explain it. Our single qubit gates are really good, but everybody's single qubit gates are really good. And right now we're working on 2 qubit gates, and we actually believe that we'll be able for the first time to, of anybody, reach 4 nines. We'll see if that's true or not. And so the dream is that if we come back to this quantum network and we make these ions, or maybe all of them barium-133, it turns out for super technical reasons, this remote entanglement rate, which is sort of the limiting step to building a quantum computer this way, may go away. It looks achievable to have remote entanglement rates, which are the same speed as these 2 qubit gates. And so now if you can entangle 2 different registers at the same speed you're doing operations within the register, there's really no slowdown to utilizing this extra resource and growing. So time will tell, but that's where we're going on that project. That said, it may not work. Right? There are lots of reasons to be worried. And so we have some other projects in our group, which I sometimes call the previous stuff your kid's qubit because it's going to be ready soon, and this may be your grandkid's qubit. And this is a subtle argument, and it's debatable, but I think that these phonon modes, this very thing that enables trapped ion quantum computing, are the problem. Right? There's mode crowding as you scale up, there's anomalous heating, other technical details. So it would be really good if you could do this without relying on this shared motion. All right? Put another way, if I could build a quantum computer without having to control the motion at the quantum level of the qubits, it'd be a lot easier. Right? I think that's probably an agreeable statement. Without going into the details too much, Wes and I worked out something, I guess this was last year. It's an idea we'd had for a long time, but finally wrote it down, that if you take and replace these ions with molecular ions, right? These things can interact directly. They can have strong electric dipole moments, and you can use that to entangle them. That thing doesn't care about motion that much. And so what that means is then I can do sort of really good fidelities at really warm temperatures. So for us, 100 millikelvin is like the temperature of the sun, right? It means we're not controlling the motion at all. We're just kind of cooling it and hoping for the best, right? Now, Berga is working on this idea of doing this with electrons, which shares a lot of similarities with this, of sort of getting away from the complexity of trapped ions as sort of next generation qubits. So I would point out that Conquin Nee's group at Harvard came up with a very similar scheme, basically the same idea, but for neutral molecules at like exactly the same time. And this, like in the stuff Berga's group is doing, would be, the sort of way you would build a quantum computer with that. One thing I want to flash up quickly for the experts is something we just finished a couple weeks ago. It came out of an idea we had with Dave Patterson, Wes and I wrote up, that I think is going to be incredibly powerful. And this slide is basically for Berga, but the short version of it is that if you have a molecule in an ion trap next to an ion, atomic ion, and you make these phonon modes near resonant with the molecular transition of the dipole states, you get a Jaynes-Cumming Hamiltonian that just falls out. It's super scalable, and it allows you to do things like read out the molecule state, entangle it with the atom, and all you're doing is changing the DC voltage on the end cap to turn on the gates and off. So we're really excited about that. All right, so you can pay attention again for everybody else. So the dream is to build something like this, that we could take these molecules, we can trap them on a chip. So this is something I haven't talked about, but we're able to take these ion traps and make them on a chip, like lithographically pattern them. They're small. We can shuttle ions around on them. People are working on this for trapped atomic ions, but the problem is as you move them around, you sort of need to move them around to solve the scalability problem. You sort of move them around, entangle them, bring them over here, let them wait, do different operations. As you do that, you heat them up. And because you need to control the motion in trapped ions, heating them up is really, really bad. But the molecules don't care. And so you can bring them together, entangle them, you can take them over, read them out with this dipole phonon idea. And this looks really, really scalable. All right. But what's the challenge? Well, so this is something we've been working on for a while, and the idea is to, get away from atoms, which are sort of boring white balls, and go to molecules, because we have all these other states that we can harness. These same states, which are vibration, rotation, and motion, complicate the situation. So I like to show this because it really accurately sums up my emotion about this field, as you'll see. I like to say the atom is this is, I think, the sixth stage of Zen Buddhism. You're on the back of the ox playing your flute. Life is good and the ox is taking you home. I think the next stage is the ox is no more. I don't really know what that means, but for right now, we've tamed the atom and life is good. In molecular physics, the story is a little bit different. We haven't quite tamed the molecule, and so that's what we're working on here. Okay, we're going to go on top. And so what we've been doing in my group is trying to get off the horns, if you will, and somewhere near the back of the bull. And one of the chief technologies we've developed for that is something we call the motion trap. So a MOT is jargon for magneto-optical trap. It's this laser trap where you shine a bunch of lasers in, and you can trap and cool atoms at basically, a microkelvin to a millikelvin, and they're just sort of held there by the laser force, right? This is a very standard technique in the field. The ion trap we've talked about. The idea is you place some voltages on these rods. It turns out they have to be time dependent, but you can trap ions inside of this. If you're familiar with quadrupole mass spectrometers, they're basically just ion traps where we put voltages on the ends so the ions can't leave. Right? But for everybody else, they're just, you apply some voltages and you can trap ions there. So what you do is you shove this thing together. When you do that, it spells the word motion, so we call it the motion trap. Actually took us 2 years to come up with this acronym because one day someone wrote on a drawer MOT ion parts, and we're all like, holy shit. And the idea is basically just like ice cools down a drink, we can stick whatever we want in an ion trap. They're super deep. They trap anything that's charged. We know how to make atoms super cold. That's our ice cube. So we don't have to worry about cooling down our molecules, right? So something I should have said, which is sort of implicit in my life, but maybe not in yours, is that to get control of stuff, they need to be cold, right? Basically, the way we do it is we just cool them down to the ground state, and then we've done quantum state preparation, right? If you're able to detect what state they're in, that's sort of the same thing as cooling, right? From an information perspective, it's just easier for us to cool things down and let it go to the ground state. So we're all about cooling. So here's what it looks like with a little more reality to it. So we have this ion trap. If you look in the middle when this thing is running, we have a cloud of calcium atoms. That's what we've chosen as our ultra-cold ice, if you will. And inside of it are the ions. This is, I think in this case, like some barium ions or something. They get really cold and they sort of order up into this little crystal. This thing here is a mass spectrometer, time-of-flight mass spectrometer that this guy, Christian Schneider, who's a research prof in my group, who is phenomenal and responsible for a lot of the great things that go on at UCLA and every group, developed this thing. To give you an idea, no one had ever been able to do this before because it's pretty hard, but Christian's super German and we just sort of let him do it. Sometimes you got to leave him alone to innovate. And so what this thing allows us to do is solve a really important problem for us, which is we want to work with molecules, right? And so here's a picture where we loaded in a bunch of ions. I think these are like ytterbium ions. And you see there are two we can't see, right? So these ytterbium ions we see because we're laser cooling, they're scattering light, we're collecting it. The molecules, they don't interact with the laser, we can't see them. How do we detect them, right? Similarly, I won't really talk about it too much today, but in my group we've done a fair bit of chemistry in this regime. I don't know if you want to call it quantum chemistry or not, but maybe you do. And what that looks like often is here's a case where we had a bunch of barium atoms. We were reacting them with a gas, and you see that this ion right here reacted and formed a molecule. He went dark. He's still trapped, he's still there, but we want to know what he is, right? And so this mass spectrometer allows us to hit a button, and then we can get every ion in the trap out and its with sub-isotopic resolution. And this has been a really powerful tool for our field. And I really can't give Christian enough credit. I mean, this thing has been built probably 10 times all over the world now, thanks to him. And as you'll see, we use it a lot. All right, so that's the system. And now let me tell you about our work sort of taming this bull, if you will. So we have to cool the motion. We have to cool the internal states. I'll talk about the internal states cooling first. That was done a while ago and sort of paradoxically was easier. And then I'll briefly talk about the motional cooling, which took much longer to figure out. And if you're into sort of non-equilibrium physics, I'd be happy to geek out with you later. This is a really cool problem. One of the most satisfying things I've ever worked on. But first, let me tell you about the internal state cooling. So the idea is that these atoms collide with these molecules and cool them down into the ground state of rotation and vibration. Right? That's sort of a prereq for doing quantum stuff with it. You got to know what state it's in. When we did this, what we found out was that the cooling rate was about 1 million times faster than what you would expect based on work that had been done in the all-neutral world, which is where most of us were coming from. And that we had some hand-wavy ideas, but it took about 3 years before a couple of theorists, Thierry Stokeland and Bordeaux, and our longtime collaborator, Svetlana, were able to figure it out. And the story is actually really cool. So this is a picture. So we were using barium chloride molecules. That's sort of our qubit. We like this because it has an enormous dipole moment. So it's really good at interacting with other dipoles. And then we have this calcium atom for cooling. All right? And we need to cool this thing into the ground state of rotation and the ground state of vibration before we can start doing stuff with it. Now, so why is this so efficient? Well, if you ask the question, what is the minimum energy of these three guys if I leave the barium chloride bond length at what it normally is? It looks about like this, right? Roughly to scale. If you ask a different question and say, what is the minimum energy if you let all the bonds sort of, free to go? It looks like this. And so what you see is that the calcium prefers to be close to the chlorine, and the barium stretches away. So during this collision, there's a strong coupling of the internal energy of the molecule to the atom. And so when the complex falls back apart after the collision, it takes away this energy very efficiently. And their theory agreed with our data. That's not important. More importantly, it is important, but the important thing is they were also able to develop a simple model that agreed with the experiment and allows you to pick sort of good partners for doing this. Turns out this isn't even important because the answer is everything works when you're working with laser-cooled atoms and ions that you would want to work with. So this thing, which was a big worry in the beginning, is a completely solved problem. All right, so now let me tell you briefly about this motional cooling. And I'll pose this question to you. Suppose I took this is a real picture. I put a single ion inside of this ultra-cold buffer gas, right? So this thing is its temperature distribution looks very Gaussian. You could actually call it a temperature. Or its energy distribution looks Gaussian. You could describe it by a temperature, this calcium, the purple thing. And you put one ion in there. What temperature does it go to? Well, there's the obvious answer that I wouldn't be asking if it was the right answer. And the answer is it goes to a different temperature than the buffer gas by about a factor of 2. And that has to do with the details of this trap. There's a driven component to the motion. These ions are trapped inside of these traps, not with sines and cosine trajectories, but with Matthews sines and cosines trajectories. And those things sort of are like cosines and sines that know about phase. And the details of that mean that it's a little bit hotter. But we can add more ions. We can add 2 and see what temperature it goes to. We can add 3. And when we do that, what we found was something that I found remarkable. And that is there's a bifurcation in the steady state energy. Right? It's not really fair to call it a temperature because your distributions aren't Gaussian. You don't have sort of, central limit theorem. You have multiplicative fluctuations. You get power laws. But the thing you would call temperature bifurcates. And what do I mean by that? It means if I put a few ions in and I say, what temperature do I realize? No matter what the initial condition is, I cool down to like 10 millikelvin in this case. But if I go one more higher to 4, 5, 6, all the way up to 20-some, the temperature I end up at depends on my initial condition. If I was cold, I will cool to this fixed point. If I was hot, hotter than there's a bifurcation point that's about 10 Kelvin. If I'm colder than 10 Kelvin, I end up here. If I'm higher than 10 Kelvin, I end up here. As I keep going, eventually the bifurcation closes and there's only one more temperature. Now, this took us a long time to figure out. We're actually able to explain it now analytically and control it in our experiments. It solves some problems that date all the way back to day melt, sort of 50 years in trapped ions. Of people couldn't. Actually, it's funny. There was a News and Views article, or no, what the APS version, the Spotlight, the PRL writes, like a month ago about this experiment that was cooling ions with cryogenics in a storage ring in Germany, and like the APS article starts off with, "No one understands why these temperatures are like this." Like, hey, nobody reads anybody's papers, I guess. All right, so that would seem very good, right? That we have control of these molecules now. They're going to solve our scalability problems. So what's the catch? Well, there's one limit that we've really been worried about for years, and just in the last year, we've been able to address it. And I'll tell you about that. What time do we end at 4:50?
4:50, we have to leave.
Okay, I'll end before that. Okay, perfect. So one of the things we're doing in cooling these molecules is we don't want the molecules to go away, right? Those are our qubits. But we have atoms and ions nearby. If you're a chemist, you're like, oh, surely this thing reacts, right? And so if our cooling process destroys our qubit, that's a bad thing. You don't need to know a lot about quantum computing to know that's a bad thing. So we chose this system for a reason. Because all the reaction products, which is the calcium sort of coming in, replacing the barium, and charge transfer or not, or just straight charge transfer, are many, many thousand Kelvin above the ground state. So at our temperatures, these could never happen. All right, so that was by design. The issue is, if you're paying attention, you realize that you can see this calcium. You can see the calcium because it's in an excited state emitting photons, right? The lasers that do the cooling promote it to an excited state, which is up here. And it's going to be impossible to find any system where this level is below these exit channels. There's just so much energy in a photon that you're always going to open some reactive channels. And so what's worse about this is that if you look at what you expect for the reaction rate for something like this, you actually expect as you get colder, it reacts even faster. And that's because it's a very long-range ion quadrupole interaction that can really reach out and pull somebody in to react with it. All right? So working with these guys, Christian and a couple of collaborators and 2 excellent grad students, we addressed this. And we wanted to really understand this because it was important to the sort of long-term future of this field. And so instead of just bringing cold things together to react, we developed a technique where we could look at reactions as a function of collision energy and not temperature. And that's important for sort of studying the details of a reaction. So the way we can do that is it's very easy for us to move an ion back and forth with just a DC voltage, right? If the MOT's in the middle, we can do it so that when the atom is going through the molecules, it's going at one velocity and only one velocity. So you're doing a collision as a function of energy, not temperature. What that looks like when you're doing it is you see the ion just at the endpoints, and here's the ultra-cold atoms. We can actually do it with chains. So these are 4 barium ions, and in the middle we've placed a molecule, and we're able to use those to pull the molecule back and forth through this ultra-cold gas just to react. It's like a reactor that we can just go over and over with until it reacts. And we can even do it with more complicated arrangements. And when we do that, here's what we found. So there are sort of 2 p states you have to worry about in calcium. One of them is this triplet state that's long-lived. And when we look at its reaction as a function of temperature, this is kind of a hard state to work with, but it's pretty clear it's going up, and it's going up about as you would expect from theory. The theory has a big error bar because it turns out the properties of the atom aren't super well measured. When we went to do the other state, the singlet P, this one is not such a big deal because we can clean it out. It doesn't really bother our experiments, but this one would kill our experiments, absolutely kill it. What we find is it goes to 0. All right, and from a capture theory, these should be basically the same. So why is that? Well, using this mass spec that Christian developed, we're able to look at all the products that we make from this reaction to try to learn something about what's happening in this chemical reaction. And what we find when we do that, we can see the calcium chloride product, the barium product. We make a table, the data is shown in blue. So basically half the time you get a barium ion, half the time you get a calcium, and some smaller fraction you get this molecular ion. We see that it agrees very well with this red, which is called phase space theory. And that's basically just state counting. You say how many exit channels are available for each one of these products. You weight them all equally, right? So that's internal states of the molecule, spin states. You subject it to conservation of energy, conservation of angular momentum, and then you just sort of weight them by that number. You see it agrees very well with what we see. So the chemists would say that this reaction is statistical. And a statistical reaction typically signifies you have a very long-lived complex. Like this thing comes together and can bang around a while. It's sort of ergodic, if you will. And so all the final states are just equally probable. So then you start to ask the question of how long-lived is this? And chemists have a way of calculating this with sort of RRKM theory. And it turns out that doesn't really work in this case because we're so cold. What happens is so this is something called a molecular potential. For those of you not familiar with it, this is just the interaction between a calcium atom and an ion as a function of R. This is just a schematic. In the ground state of calcium and its first excited state. The bound states of this potential are our molecules, right? And so we start off, we're just scattering on these potentials. So we're scattering in this excited state, which would react, but because we're so cold, before they can get to short range, which is where chemistry happens, they just spontaneously emit. They shoot off a photon, relax to the ground state where they can't react. And so the reaction is just suppressed and shielded by the spontaneous emission of these states if we're really, really cold. And so when you include that in the theory, you get a much better agreement. It's qualitative, maybe not quantitative. And so that was some work that Pratik led. And then at the same time, we did something that Mike led to look at a system we could control better. So instead of a molecular ion, we use an atomic ion, which could also react. We have sort of perfect control over this thing. And there you see that we also see the suppression, and it agrees very well with what we expect. So if we understand it, we should be able to turn it off. And this might actually be a useful technique in chemistry, I don't know. We applied a laser that dresses these potentials. And so at short range, it can promote atoms which are in the ground state near the zone where the chemistry happens in these potentials. So we should be able to turn the reaction back on. And when we do that, we see that we can do it both as a function of intensity and laser frequency, and it agrees basically with what we expect. So the takeaway there is that some fun chemistry. Oh, and we did this with, I should say, with Svetlana and her postdoc Ming. Svetlana's at Temple University. We collaborate with her all the time. The takeaway is that this chemistry isn't inevitable after all, and we finally have control of these molecules. This is something we've been working on for about 10 years and sort of systematically checking these things off. So we're able to bring them together, cool them, and to keep them from killing each other. Right? And so we're really excited about this for quantum computing, but the problem is spam is hard. And in the last 6 minutes, is that okay? Or should I end more quickly? 5 minutes? Last 5 minutes? You can tell the Germans. I want to talk to you about about what I think about that. So to remind you, spam is state preparation and measurement, not the meat product. That thing is really hard for molecules, and we just haven't figured it out yet. It may be that we got lucky, and a mystery in our lab may be the solution to this. This is kind of cool. This was something just for the grad students that nobody in my lab wanted to discuss. It was something that happened in our experiments. It was a mystery to everybody. It was like, don't tell Eric, he'll make us look into it. And it's just gonna waste our time. But this guy, who was an undergrad at the time and then went on to be an amazing grad student who just defended, was the low man on the totem pole, and they were like, Pratik, go look at this. Pratik got a science paper out of it. So remember that. So the mystery was this, that we put molecules in these traps, and after a long, long time, maybe 10 minutes, atoms, these were barium atoms in this trap. After a long, long time, a lot of them went away. And they were forming this molecular ion, which thanks to Christian we could easily measure, was barium methoxide. which sounds weird, but it turns out it's a reaction of barium with methanol. We clean our vacuum with methanol. There's maybe 10 to the minus 10 torr of methanol. And if you run the numbers for how long this takes, it's about right. So life gives you crazy molecules. You decide to see what can you do with them, right? And so we turned on this calcium mot to see what happened with them, and they went away. And they formed something super heavy, and nobody could figure out what they were. Like, we have the mass, we know all the things that are going on. It's this thing plus a calcium atom, but nothing that made any sense would add up to this mass. We took every laser we had and just kept shooting it into this thing until eventually we broke it apart. And we would see that it would make a calcium atom and a barium oxide. And what that is this is a barium oxygen calcium molecule. Now the physicists are like, well, why didn't you think about this? And the chemists are like, because that's a crazy molecule, right? Like, if you think about it, like, barium oxide is like a super happy thing. Like, barium has 2 electrons, oxygen wants 2, calcium has 2, oxygen wants 2. Like, it actually turns out the neutral of this exists. So in this thing, what's going on, and I'm going to skip this in the interest of time. If you look at what chemists call the highest occupied molecular orbital, sort of the last electron, you see that that lone electron doesn't have anywhere to go. And he's just kind of hanging out on the calcium. And he looks like, very much like, the electron that's normally on calcium in its ground state. In fact, it has a transition very, very close to the normal transition frequency of calcium. And so what this means is that we have this dream of doing this atom-like state detection, because I can excite this electron, and then it will spontaneously emit, and it will come back to the same state. So this is very much like what Berg is doing with his aluminum chloride, but this is an ion version of it. And these are sort of more complicated, maybe not as good candidates for it, but it's what we have. And so we're now working towards this in a collaboration that I call the electron on a stick collaboration with a couple of quantum chemists who are really good at these structure calculations, Nick, who I think, and John, who Berger knows well, and these guys. And so I'm pretty excited that we're finally going to solve this last problem. All right. That said, it may not be good enough. And this is what I want to leave you with. We're to the point in quantum computing where it used to be if you had any soup, you were happy, right? Like, you had a qubit, you could do anything, it's fine. We're really to the point where we need something that's just right. And like, the technical details really matter now. Like, if you have some qubit and it turns out that its transition frequency isn't quite right for microwave electronics, just throw it in the trash. Like, there's other stuff that's going to be better. Like, we got to get everything just right. On a broad scale, where we're at, I think, is the qubits we have are either too hairy or too delicate, right? These things, they're just non-identical when they're man-made. And that's just proving to be a problem. Probably this will never work. These guys, they're just so hard to scale up. They're too delicate. A lot of stuff messes with them. We really want to be in what I call the robust and bald region of qubits. Maybe that's for personal reasons, but... And so I want you guys to think about how we do that. Nobody has any real ideas right now. The chemists are coming up with stuff. Most of it's terrible, but there might be onto something. So here's the criteria you should remember. And here's my thought on the problem. We need something that's identical. That means we can't make it, right? We're going to have to use chemistry to make it. It needs to be bigger than ions, or trapped atoms, I think. And so we need to use some sort of chemical synthesis to produce things that are identical, right? And they can be big molecules, and we need to be able to extract them so they're pure. I know that's hard, but like, maybe that's conceivable. And you can imagine things like you have, some benzene rings, maybe some qubits on the end of it. You have some magic molecule that you hit it with light, and these things bend. I mean, these things exist. These things interact. You can hit it with light again, bring them back apart. You can imagine building some functionalized molecule that is my quantum computer. Look, this is like really dreaming, but I think that is how you really build a quantum computer that's scalable, is to use chemistry. So you could think about that, and I just made my screen blank. Oh, and I will end here. Hopefully I told you about quantum advantage, why everybody's excited, also why you should be worried. Our work with radioactive qubits, our work taming molecules, and then I hopefully got you dreaming about how we should really be doing that. All right, thank you guys. Usually. Yeah, I mean, it depends. The one limit is the MCP detection efficiency, which is normally, so the ions hit some sort of charge-sensitive detector, and those things are pretty close to 1, but not perfect. It's pretty easy to get above 30, 50%.
Can they like interact with each other during the flight?
Not so much. We get them out of there real quick. But it is something, so we actually, one of the reasons this thing works so well is this whole thing's like this big, but we have like the isotope, the resolution of a mass spec that's like huge because we're starting at about basically 0 Kelvin. And so there are a little bit of effects like that, but they're manageable.
More questions? Yeah, Chris.
So these schemes with like phosphorus ions and silicon stuff, are those still too hairy?
I mean, that's maybe a discussion for dinner. I don't know. I mean, like if it's near a surface, it doesn't matter if it's hairy or not. The surface is hairy, right? So yeah, but at the level of, I don't know. I mean, it's debatable, but my theory is that it's probably too hairy. But look, we hope we're wrong about all this, right?
Very naive question. Could you explain how a quantum computer calculated, let's say, 2 + 3?
I don't think you would do that.
How would you realize it with your eyes?
So you wouldn't really do that with a quantum computer. I mean, if you wanted to, you could use those internal states just as bits and do the normal. I mean, I couldn't explain to you how to use NAND gates to do 2 + 3. It'd take me like 10 minutes. But you could do basically that. Yeah, I mean, you have a computation spacer register. You have a set of gates. You can just define a circuit, and you do gate this, gate that, just like you would do with NAND gates in a classical computer. And then you have to read out, and you want to read out, hopefully your state has a high probability of projecting into 3 and not 8, or whatever your answer is supposed to be. It's actually funny. So Ike Schwang, who you may know is one of the fathers of this field, when he was at IBM, factored 15 into 3 and 5 in this NMR computer, or NMR quantum computer. It's like the first example of Shor's algorithm. And I remember the first conference when he got up and said, I can say with 70% probability, 15 equals 3 times 5.
More questions? I have one last one for you. It seems like you get a lot of results and answers on the reactions, kind of on the end products. Do you have any chance to access the intermediate pathways?
So I think with ions it will be very difficult. The collisions are quite dramatic because you have the charge pulling in a dipole. Con Quinn, you know Con Quinn, me at Harvard, of course, she is, in her neutral experiments, they are starting to see these intermediates because there the collisions are like almost not even collisions because they're so not attractive to each other. So right now, I don't think with ions you're going to do that, but I think with the neutrals, that's already happening.
You can actually make a movie of the chemical reaction.
I think so. I think she's really close to that. And she has a VMI setup, a velocity map imaging setup inside, so you can really map out what's going on. It's pretty exciting, I think.
All right. Anything else?
Do you have any sense that quantum computing, the idea's been around for a while, and it's sort of puttered along, do you have any sense, I mean, is it going to be, when are you going to do something useful? Is it 5 years?
No, that's a great question.
Is it 5 years, 10 years?
No, I don't, it may be never. Like it literally could be never. So there's different answers to that question. So the quantum simulation stuff, that's already happening. We're already doing things, not me, but other people are doing things sort of at the edge of what can happen classically. And I think as physicists, we're going to learn about quantum many-bodies. So that, I think, will happen. It's happening. It'll happen over the next 5, 10 years to a level that's really transformative, I hope, for condensed matter physics and quantum many-bodies. But that's not really the question you're asking, I think, which is what are these things that are useful on a broad scale? And the answer may be never. If the answer is, we have to get to Shor's algorithm where we're factoring prime numbers, God, that looks hard. That looks 10, 20 years away at least. The hope in the field is that people, as these hardware are coming online, are going to come up with new algorithms that can be run on current hardware to be useful. So these ideas of studying chemical structure look promising. They're not really useful yet. There is an algorithm that has recently been invented for generating certifiable random numbers. So you ask a server for a random number, it gives it to you. You can ask it another question, you can prove that it's a random number generated by a quantum computer based on the answer. People pay for random numbers. So Google actually has some plan of using one of their processors for random number service. The one that they just used for quantum supremacy, they actually state in the paper, this same thing can do the random number thing. Is that useful? I guess. But, so the answer is, to really get to the gate-based quantum computing looks far, far away. Right now, there's maybe going to be some small things like this that come about. And I don't think anybody knows. And that's sort of the danger of everybody jumping on this bandwagon right now. But maybe it's good too to have more people thinking about algorithms.
I mean, certainly an absolute random number is useful, right?
Right. Yeah. But I feel like I could make a random number with some electronics that's like super random. I don't know. Anyway, yeah, but you're right. People pay for it. Yeah. Oops. Yeah.
So why do we array of the ions to move the molecule across?
Oh, so in that case, the reason we were doing that is we wanted to keep the molecule cold. It turns out in these traps, there's all sorts of lies I told you. These things heat up like crazy if you don't keep laser cooling on. So we basically have these 4 atoms as chaperones. The laser makes them cold. By association, they make the molecule cold. And what's that? Yeah, well, they're interacting always through the Coulomb interaction. And so they stay sort of cold through that. It's a collision. I mean, it is. It's just a collision mediated by Coulomb interaction. So they're like chaperones for the molecules. If we don't do that, the molecules heat up, and it's kind of a pain.
I was going to ask, just how many qubits would industry need for industry to do industry things?
So it's a good question. I mean, I think people are hoping that at a few hundred qubits, we're going to start to be able to do things that are interesting. I don't think people really know what those things are yet. Shor's algorithm is way past that, thousands to millions. And depending on if you have to do error correction works basically by just adding a bunch of extra qubits to make 1 qubit, to make it sort of fault tolerant. So the answer is out. I mean, people give talks and they say, if we can get to a few hundred, we're going to be able to do great things. But it's not super clear what those things are. Yeah. Sorry, I don't have a better answer. I just try to be honest.
Yeah, unless there are any more questions. Thanks, Eric, again.